Welcome, everyone. So we have a session on building and running HPC solutions with HTC-Grid. We'll look at what that means, why this all started, and how did we solve for it. So if you work for any of the big banks or financial services institutions, you'll know that there is this thing called a risk workload that happens in the end of the day. Usually, they will have also intraday or on-demand risk. That basically runs a lot of calculations, and you have a potentially sizable but limited compute capacity on-prem. And as we've seen, a lot of customers, they tend to need more compute than have available. So a lot of these banks have been looking at cloud as a way of getting access to more capacity for these HPC workloads. We started HTC-Grid about 5 years ago as what we call blueprint, because we saw a lot of our banking customers try to build a more cloud-native approach to doing HPC. And they went to the drawing board and thought about how do we do this, and more or less everybody kind of resulted in the same design. So we wanted to bootstrap this journey for them so that they can build a solution or build on top of our solution easier. So HTC-Grid was started, sorry about that, as a high-throughput system. And the reason for that is, if you look at the traditional risk workloads, there tend to be a lot of short-running tasks, but a large number of them, and a smaller, long-running task. Thank you, because I was echoing like crazy. So because of this, we do have this high-throughput requirement for this workload. So HTC-Grid, high-throughput compute grid, was started with that in mind. Now, when we designed HTC, we had some design tenets that we considered. I'll start with some of the simple ones. So we wanted, obviously, to make it cloud-native, because there are vendor products that exist out there today that are used for similar workloads. However, they were not built for a world of flexible, sizable compute. They were built for a static on-prem capacity. So they don't really do scale up, scale down, et cetera, really well. So cloud native and using cloud native service is one of the main design tenets that we considered. The throughput and low latency, as I said, is another very important consideration for such a system, because we need to be able to handle those large number of short-running tasks. So we have tested HTC-Grid up to 30,000 tasks per second. So what that means is, if you were to run a task that did exit zero, nothing, it just finishes as soon as, so removing the calculation time aside, as a system, HTC is able to handle 30,000 tasks per second. We have not pushed it to its limit. This is just what we've tested it to. It can actually go higher. That also means that the end-to-end scheduling latency is very low. So from task submission to the task being finished, it's actually 0.3 seconds. So it's fast enough, including for real-time workloads. It is unparalleled scale and unparalleled speed. Another thing that we wanted to do is make it modular. So you can remove components, and you can actually replace them with other similar components from other services as well. I want to talk about the compute is Lambda thing, because that is what confuses people. So AWS has a service called AWS Lambda. We are not doing that here, but we're using the Lambda API. So that means that when you schedule tasks, all you have to do is say, this is my input, this is what you need to calculate, give me the result. That's it. The API is standard. So looking at a architecture from a bird's eye view, these are kind of the components that are used. So here we have the client side of it. Most of these systems come up with a SDK that is actually used for actual submission of the tasks, and it knows how to speak the language of the system, whatever that means. And the connector library knows how to go to the control plane and knows how to submit tasks. So we split the task definition and then the task payload because the communications are basically REST, and there is a limit on how much data you can send in a REST request, right? It's 256 kilobytes, which is not sufficient. So we wanted to give customers the ability to package data together with a task that you're running the calculation on, but then we store it separately to make it easier for the system to actually reach that high throughput. So the control plane is comprised mostly of serverless services to actually make this also as fast and as actually able to scale to that large scale, because everything happens in parallel. There is no component that becomes the bottleneck, because every single flow basically triggers its own components. And then the compute plane is modular. As I said, from a design perspective, we wanted to make sure that you can swap things for whatever you need. So the default deployment uses EKS, but there is nothing stopping you from using EC2 or ECS. So EKS is our Kubernetes offering for AWS, EC2 is just virtual machines, and ECS is a container service as well. And then the data plane, as I said, is where you would send your task payload with. However, it's also where you store results, and that's also another modular portion of the architecture. So you can choose to use something like S3, like a bucket system, but you can also use Redis, you can use FSX, and so on. So it just depends on like the speed requirements and the size that the data that you send with. So if we were to zoom further in, like it's the same architecture, just like taking a deeper look. As you can see in the control plane, the only thing that the calls do is through a API gateway called Lambdas. So Lambda is function as a service, and every time you say submit, it sends that data through the API gateway, calls the submit API. The submit API would store that data on DynamoDB and also on SQS, which is just a queue. And then we use that queue as a means of driving the scale up, scale down of compute. And then workers come up and they just pick up tasks from that queue, do the calculation, and then store the results. If you remember, I said the Lambda API is how we schedule compute. So if you look at this here, this is the EKS, the Kubernetes variant. And then our worker is basically a pod with two containers. And one of the containers which does the work is this Lambda container, and that has that Lambda API. The reason for that is when you build such a system that is meant to integrate with all of the different QR libraries and customers that we have out there, it would not be possible for us to change this API every time a new QR library is ingested. So as far as the system is concerned, that Lambda API is the one that the system speaks, and the integration between your QR library specific to your asset class or department or LOB, whatever, happens here in the Lambda container, and that is just internal to your deployment, doesn't affect the rest of the system. That was one of the design patterns that we used that actually made it possible for us to also reach that scale. So I'll just do a quick demo. What I have here is I will look at the logs of the agent container and the Lambda container. As you can see, for example, here, it is just showing the same Lambda API. You get an event, you get a result. That's the standard. And we're also going to look at how the cluster is performing. So currently, we have one single worker running. And what I'm actually going to do is send a job with a lot of tasks. Now, we use, if you know, Quantlib, which is an open source quantitative analytics library, to actually do a real life pricing of some European and American options. And the demo is basically sending 100,000 calculations to be done on the grid live. So all of these crazy numbers that you're seeing here is all of the different calculations that I wanted to do. And now you'll see that while the system is already submitted those tasks, now I'm saying, okay, give me the results. Like, how am I doing for results? You'll see here that the number of tasks in response keeps increasing. That is, I already had this one single worker that said, I am running, there is stuff in the queue, I'll pull up and start doing work on that. And you'll see that it slowly kind of chugs along. But the system will soon realize that I actually need more. So here you'll see that now my target for HPA, which is the component of Kubernetes that does auto-scaling for pods, increases based on my queue depth. So it says, okay, my queue actually has a lot of items in it. I have about 1,000 things to work on, so I need more pods. So it will automatically increase the number of pods, and then they come up, join that queue, start picking up tasks, and do work. So if we look at this from a simple Grafana dashboard, I'll just do 5 minutes. You'll see that we were like doing nothing basically. It was active agents, just one, and then it automatically starts picking up and scaling the agents up. And then you'll also see that my task completion rate increases because I now have more workers and I'm able to finish work faster. And the cluster will automatically, there you go, we already have whatever that is, 16 pods across different nodes. And then the number of tasks that gets returned is then a lot bigger because you have more workers chugging along that queue. It works in a FIFO aspect, so first in, first out in the queue, and we're able to finish them. So we will let it go along. I'll just cover a couple more slides here. So what do we want to do? HTC-Grid was started at AWS as an open source service, as I said, because we saw all of our customers kind of go through the same hurdles, and the vendor products that are out there are either end of life already or in that journey. They're about to die. And there is no really good alternative out there, so we wanted to build something for the community, for our customers or financial services customers to be able to have a suitable alternative for the world of the cloud. That being said, we wanted to collaborate with the rest of the community, both financial services as well as other CSPs, to have them work together in this project, because the whole of the industry has this problem. It's not AWS specific, it's not a specific financial institution. So we wanted to donate it to FINOS to give it the new home where multiple firms can actually collaborate on this. One of the biggest things that we would like to achieve is make it cloud agnostic so that this works across all of the clouds. Not the case just yet, but we're hoping to make that happen, and we're trying to work with other CSPs on this. The modularization will go even further because we want to make this deployable on different architectures, including potentially on-prem if need be. We also have, as I said, tested it to 30,000. It can go further, we just haven't done it. We have tested it to 80,000 worker nodes, which again, it can go higher, but we haven't had the use case yet. Some management and observability changes, hopefully into the future, UI, and some cost and visibility control as well. So if you are interested, please reach out. If you have questions, feel free to ask them here. I also have a project booth table just across the street. Like when you come out, it's literally in front of the door. And if this is something that you find useful or interesting and you would like to contribute, then please come and say hi. We would really appreciate that as well. So let's look at our run. It's probably done. There you go. So as I said, I sent a 100,000 tasks pricing of European and American options to the cluster, and it finished in whatever that is, like in less than a minute. It automatically scaled up. As you can see here, we started at 1. It automatically went to 16, 64, 250, finished all of the calculations, and then in about a minute, it will start scaling back down again. I have configured it for not so aggressive scale down. And as you can see here, like it was doing all the calculations per every worker. And this one is purely that Lambda API. So with that, I'll stop. Any questions? Yeah. So Adam also works for AWS. He's my colleague. He's asking about a hackathon, which we did last week, and we added some new features to the dashboards that we have available for HTC to show this like lifetime. So again, as I said, if we just look at the time of this run, it went from 40 to 43, reaching its peak here. And the actual time, like for about a minute, it seems that it like slowly started. And the reason for that tends to be that when you say computer start, it takes about a minute for that to happen. So while the system did recognize that there is work to do as soon as, we have to wait for the initial instances to come up. But then once that happens, you can see that it actually scales up fairly fast and then does all of the calculations and then scales back down again. So like that basically translates here. That's the number of agents that we scaled up. Any other questions? Okay, thank you very much. Hope this was useful.